Hello and welcome back to Geology, and today I want to start off with Chapter 5, which are volcanoes and volcanic eruptions, and just some general definitions. We know that a volcano is either an erupting vent, right, or mountain that was built up by the products from an eruption, right? And there's some old terms. There's a term Vulcan for kind of the god of fire, right? But there's also an island called Volcano in the Mediterranean, right? So there's different sources of it, but we want to know the volcano is really either produced by a volcanic material or an erupting vent. Now, your book starts off with a very important eruption in 79 AD of Vesuvius in Italy. And this is famous because it destroyed two towns. It destroyed Pompeii and also another town called Herculaneum. And these towns were buried by pyroclastic material, right? And so we all know what pyro means. Pyro means fire, right? But this clastic, we want to point out here that this clastic term means, it's a Greek term. So we'll say Greek for broken. So somehow we're going to have material broken by fire. So really what happens is that there's a shattering, right? So because this type of magma is very rich in gas, when that gas expands very rapidly as the eruption occurs, it shatters the magma, right? So that's what we call pyroclastic material. And we all know that pyroclastic material is going to be part of a series of volcanic material called Tephra. So Tephra is material that's ejected airborne out of the volcano. Remember, the other type of volcanic material is lava that pours out of the volcano, and then there's also volcanic gases. So this eruption of 79 AD, pretty catastrophic. We call it a Plinian eruption, and Plinian eruptions are very gas charged, and they can send pyroclastic material high up into the troposphere and even up into the stratosphere, right? And so this pyroclastic material erupted the volcano and came cascading down and overran the towns of Pompeii and Herculaneum. And it literally entombed the town, preserved Italian, really Roman civilization during that time. And archaeologists began excavating these ruins in the 1700s, about 1748, and really kind of got more organized in the 1800s. But in their process, they discovered that there were many hollow openings, right? And they decided maybe they should fill some of these hollow openings with plaster, and they realized that these plaster materials was actually the entombed residents of Pompeii. So if we look at the PowerPoint here, right, so volcano, we talked about volcanoes here. This is actually an artist's depiction of this Plinian pyroclastic eruption. In fact, this we call it Plinian because there was a Roman ship's captain who was named Pliny the Elder, who witnessed this material and wrote about it in his ship's log. Nonetheless, it's named after Pliny, really Pliny the Elder, who described it. Now, so here's a plaster mold or a cast, that is, of one of the inhabitants, right? They found, people in various positions. They've even found dogs. And apparently the volcano, after the eruption, really suffered a catastrophic collapse. So this eruption is similar to the eruption that occurred in 1980 at St. Helens, right? The only difference being here is that the towns of Herculaneum and Pompeii were right at the flanks of the volcano, whereas the towns around Mount St. Helens were much farther away, right? Now, basalt eruptions, this is actually lava coming out of Mount Etna in Sicily, and they're important for many reasons. One in particular is that they bring many nutrients to the surface. We know that volcanic soils are very full of nutrients, are good for vegetation, good for grapes. Right here in Northern California, we have Sonoma County, Sonoma and Napa. That's one of our main wine growing areas, for grapes. And we have a volcanic field up there called the Sonoma Volcanic Field, right? We have three products. And so three products of volcanic eruptions. One are these lava flows. Two are these pyroclastic debris materials. So, and this is what I call tephra. So there's lava flows. Remember, the lava pours out of the volcano, flows down the flank of the volcano, whereas a tephra explodes. So this would be tephra in this picture here. And then the other material that your book mentions are volcanic gases, right? So if we go back to our go back here to our document camera, we see that we have the lava flows. And so remember, these pour out. And we could also see these are going to be lower gas content because they're not exploding out, right? So imagine shaking up that soda bottle or champagne bottle. As soon as you uncork it, the pyroclastic tephra comes out, right? But then there's still material left in the bottle. That'll be the lava flow. It's a little bit lower in gas content. Still has some gas, but not as much as the exploding material. And remember the pyroclastic debris here is going to be our tephra, right, which explodes and flies through the air. And then we have volcanic gases. Important gases include water vapor. Little arrow means that it's a gas. We have carbon dioxide. We have that stinky hydrogen sulfide gas, right? That's a rotten egg smelling one. And a variety of other gases. I'll mention more of those later, but those are three important ones there. Why are the lava flows not all the same? We have some rubbly ones, some very thick ones, some very stubby ones, some very long ones, and some that move very fast, right? And really, it has to deal with this viscosity. And think of viscosity as the stickiness or clumpiness of the lava. For example, like honey is pretty viscous. Water is fluid. So something being fluid is kind of the opposite of being viscous, right? And so the composition of the magma will determine how viscous. That's really one of the most important ones, and it's really this silica content, SiO2, right? How much silica does this magma contain? So obviously the felsic magmas are going to be viscous, right? Whereas the mafic magmas are going to be fluid, right? So those tend to flow much farther away from the volcanic vent. So usually when you're looking at a felsic volcano, because the magmas tend to stay near the volcano, the volcano is going to have a pretty steep profile, right? Because the magmas don't go very far. The lava is not flowing very far from the volcanic vent. But for a mafic volcano, you'll see that the volcano is going to have a very, very broad profile because lavas are flowing very far from the vent here, right? So just by looking at the volcano, you can actually determine whether it's more felsic or more mafic, right? And then later on, I'm going to talk about this process called silica polymerization. And just think about this polymerization as a fabric. So what tends to happen as these silica tetrahedra end up linking to each other, holding on to each other, sharing the oxygen, and making chains and rings of silica polymers. And that tends to make the magma stiff, right? So I'll mention that more in a little bit here. And then one of the first things we'll look at are these basalt lava flows, right? So they're mafic. They're going to have this low viscosity, which means they're going to be fluid, right? They're usually hot, right? Hotter temperatures. Remember, basalt lava is anywhere something greater than 1200 degrees centigrade, maybe down to about 1100 degrees centigrade. So it's going to be quite hot. So they move pretty. So obviously, the hotter it is, the farther, the faster it can move. And when it's flowing down steeper slopes coming off the volcano, they can move up to about 30 kilometers per hour. Most flows reach a few kilometers from the vent. Some can reach over 600 kilometers. And the reason they could reach, so far, in fact, here I have, they usually go 40 to 50 kilometers from the vent. So when you're looking at this, they're really going quite far. And the reason they're going so far is that they're insulated in lava tubes. So I'll have a couple of diagrams that show something about lava tubes here, right? And then as we go along, so here it is. I have it up here, lava tubes. So what happens with the lava tubes is the size of the magma, because they're in contact with either the ground or the air above it tend to cool and make a crust. And so almost like a pipe. And then the crust insulates, allowing hot interior to flow, right? And you get this tunnel or lava tube that develops. And so what happens, because the lava is fluid, right? It drains out and leaves this hollow tube behind. So that's how these lava tubes form. And then let's look at there's a couple of terms here. Pohoi lava, lava. These are Hawaiian terms. Pohoi lava, you can think of this as a higher gas content. So remember that gas also helps it flow a little bit faster, because remember, gas tends to break up some of these silica polymerizations, right? And then it's gonna be a ropey lava, and I'll show you some pictures of that in a moment. Whereas is, and then we'll talk about columnar joints here in a moment here, and then we have pillow lava. But let's look at the PowerPoint here. We'll look at some of these here. And so as we go along here, remember silica content viscosity controls the shape of the volcano. So here's a diagram showing a basaltic mafic lava flow flowing 10, 20, 30 kilometers from the vent, right, to make these broad volcanoes. An andesitic, which is intermediate, got this stubby lava flow, not maybe going 6, 7 kilometers, 8 kilometers from the vent, not as far, because it again tends to perch up near the volcano. And then here in the felsic, well, the felsic one tends to pile up right on top of the volcanic vent here, right? And then this is actually showing some basaltic flows, so you can get these plateaus. In fact, this is coming off Hawaiian volcanoes here, right? And then lava tubes, right? So here the top cools because it's up against the atmosphere, the air, and then the flow keeps continuing. Whenever there's a ceiling collapse of the lava flow or the lava tube, you get something called a skylight, right? And then so these conduits for these basaltic lavas. Then as we go along here, here's a good example of pohoi lava, these ropes, right? And so again, this is a little bit more fluid, faster moving, a little bit more gas in this type of lava here, pohoi. And then for the lava flow, you can see it's the jagged surface, a little bit more rubbly, again, a Hawaiian type mafic lava. And in fact, they solidifies with jagged, sharp, angular texture. Forms when hot flowing basalt cools and thickens and crumbles into these jagged shards. So there's and pohoi lava. Okay, well, let's pause here for now, and we'll continue in a moment.